Every one of us, I suppose all of us here are growing older, and I suppose that every 100% of the people that stayed here are interested to grow young, to grow young tissue in the body of an adult. This is something that we have been working on in Biochange for the past 6 years, and we have some really interesting success that I will present here today. I'm Ishay Attar, I'm the CEO and founder of Biochange, biomedical engineer here from the Technion. So we've developed a technology in Biochange which we named cell foam, a foam for living cells, and what it is, it's a scaffold technology which actually it's a foam, it's an enzymatically cross-linked foam. We use microbial transglutaminase to cross-link it for various reasons. It's not like the small molecular weight cross-linkers, it doesn't have any free radicals. It's fully biocompatible and there's no cellular toxicity. We've evolved the cell foam technology into two medical products that we are now working on and bring them to the clinical phase. The Revolette is for skin regeneration, or in other words, turning aged skin into young again. And the Regam for treatment of an unmet need periodontal disease, which is, I will elaborate about those. We also have veterinary products in the market, already in sales. One is the vet foam for treating urinary incontinence, and the other one is the Regam vet for treating periodontal disease in dogs, because our best friends, they also suffer from gum retraction. Our technology can come in 3 physical shapes. It can come as an in situ cross-linking like foam, hydrogel foam. It can come as a solid 3-dimensional implants, and we can also micronize the dry implants and place them in a syringe, and this is our aesthetic product actually, the biostimulator. And we can also bioprint the product, and we are looking forward to collaborate with you in various applications of this bioprinting of this technology, with or without cells. We have a booth outside that you're welcome to visit us after in the coffee break. So, so the cell foam, actually what we're doing here, we're trying to inspire from nature. We're trying to kind of imitate what nature is, how nature is stimulating tissue to regrow and repair. Our cell foam technology, actually, when it's placed inside the tissue, it stimulates it to repair and regrow itself. And it works in various tissues that we've tested it. First of all, you see the foam, it's really a random structure with an abundance of, well, the surface area is huge, and it has an abundance of RGD, or integrin attachment sites, so obviously it's very attractive to the cells. But that's not the whole story. We'll get to the interesting part soon. The elasticity of it, really, when it cross-links, when it sets, is really very similar to soft tissue. Young modulus is around 1 to 8 kilopascal, and it's very elastic. It can be stretched like 2-3 times its size. Interestingly, it also stimulates bone very well. We've done that too. So why we use gelatin in our product? Well, gelatin is probably the oldest commercial biomaterial. It's been used since the 1950s as an implant. So the FDA and all the regulatory authorities have a very long track record with it. They know it. It's very safe. The immune response is benign. It's a very benign immune response. And it's different from xenogenic collagen. It's important, that's why I made this slide, so it's important to make the difference. So, although gelatin is derived from collagen, it doesn't exist in nature. Gelatin is hydrolyzed collagen. It's cooked overnight in a very high temperature with acid or with a base. And it loses the helical structure of the collagen, and all those antigens are shed. Also, it has no aromatic amino acids and much less N, C, and N-terminus telepeptide availability. So the immunogenicity of the gelatin actually is much lower than that of xenogenic collagen. Also, we cross-link those gelatins, and that makes it even lower and even safer and even less immunogenic in the tissue. I will show you some of those histology slides. In our presentation, in my presentation here, we will focus on the in vivo data, but we also have a lot of in vitro cells culturing data. So what is a tissue? Okay, tissue is cells in the scaffold programmed to grow from the age of -9 months in humans until the age of about 20 years old. We're growing the tissues. But then after the age of puberty, 20 years old, we just degenerate. We lose, in the skin, for instance, it's about 1% every year, unfortunately, and there's no turning back on there's no real way right now to turn back that degeneration. And like I said, what we're trying to do here, we're trying to stimulate the aged or even adult tissues to regrow that tissue or later on organ. Excuse me. So what I'm showing in this slide is the magic of life. I mean, most of that growth, when is it happening? It's happening in the embryonic phase. When we, and in this case the zebrafish that's imaged here, turn from a bunch of a ball of cells within, you know, in the zebrafish it takes 1,050 minutes to turn into a full organism with all the tissues and everything, all the details, everything is already there within 2 days. And that makes it really easy to research and to try to understand what is going on. So there's been a lot of research in the past 50, 60 years about the biochemical signals, about the genetics that are involved here, and we learned a lot, but we still cannot make this happen. We cannot make a ball of cells turn into, I don't know, a liver, or a heart, or a kidney, or something else, or a retina. So we need to go and try to go around, try to do a kind of printing, or find all kind of solutions. But there's some interesting insights that have been recently uncovered about something here which is missing in the knowledge, which is the biomechanics. The biomechanics signaling between cells seems to be something, a very important element here in the formation of the shape. So tissue that you've seen is really it's the smartest material. It's self-shaping, functional biomaterial. It shapes itself. It knows how to grow, where to elongate, and which tissues to differentiate to. So let's think about what kind of, how can the structuring be formed? So we know several ways. There's not an infinite ways to do it. For instance, material addition, additive manufacturing. Is this the way the embryo that I showed you, is that how it's forming? No, actually I don't know any animal or life form that replicates itself by additive manufacturing. So when we think about the nature, maybe this is something we should kind of put our minds to. Is it forces that shape, like clay molding forces? No, it's not. We thought, scientists thought that it's clay molding shape. It's internal forces inside there, but that turned out to be not true. So what is the other option, which seems to be the right one, is the casting. It's changing the material properties where we want to grow and elongate. So each one of those cells, actually we have a smart materials with tens of trillions of cells, and each of those cells is a processing unit. It receives biomechanical signals and biochemical signals, and it has this program running, that's the DNA, and then it knows what kind of actuators to know what to do with those signals. And this is what we've seen in the embryo. So recently, there's a physicist, his name is Oger Campas from UC Dresden. He's the first one to actually image what's going on in the embryo in live, I mean in 4D. So he injected ferromagnetic oil into the extracellular spaces in that zebrafish embryo, and he looked at the forces, okay, that's going on in the embryo during that elongation. He discovered that actually the tissue, it behaves like a three-dimensional foam. And that fascinated us because it's really, it looks just like our foam actually. So that foam is tingling all the time. And at the elongation, at the axis where it elongates, the posterior and anterior sides, There's uncaging of the foam, fluidization of that foam, or change over the yield stresses by the cells. So the cells that receive those signals actuate, they change that, they uncage the foam, and then they cage it when in the parts that they don't need to elongate. So physically, we are talking about some kind of a foam in the embryonic phase, and perhaps our foam, the cell foam, activates this kind of biomechanical stimulation when we are injecting it into an adult tissue that doesn't grow anymore. We see growth, and I'll show you some of that. So in the first case, and I've selected just a few, we have a lot of those various tissues that we've tried it on. We can see a rat skin 1 month after injection of the cell foam to the hypodermis. And you see the foam in red, this meson-trichon staining, so the blue is the collagen and the tissue. And you see ingrowth of the new tissue into the pores of the cell foam. You see new blood vessels formed. We don't have any conduits or anything. It's actually, there's no cells. We've just injected the foam in, and it stimulated this tissue to regrow. Although it's an adult, we're all injecting this to adult, not to young animals. And we don't see encapsulation. So tissue response is perfect. We've seen what we wanted to see. We've seen stimulation. I'll show you what happens after. This is like 150 days later, but in a pig skin now. So a larger animal, different species. We tried this with various species, by the way. In this case, the material goes away because there's a sync between the degradation profile and the buildup of the new stimulated tissue. And you see an engineered skin tissue growing where it shouldn't be growing, in the hypodermis of a pig. There's about 6 millimeters thick in this case. It's a lot. And we've asked ourselves, well, the dermatologists that we work with asked us, is this scar tissue? Is this colloid? What kind of collagen? What kind of tissue are you generating or stimulating there? So we've done some staining. And we've proven that this is exactly like young tissue. We have more type 1 collagen, this is a good type. The type 3 is the one in the colloid. We have elastin fibers being generated. And also the morphology of young collagen is wavy collagen fibers. You can also see in this slide, the dense darker blue is the pre-existing collagen, and the new, more sparse collagen on wavy is the one that's new, that's been stimulated. So we've also compared this to existing biostimulators that are used today in the market, in the dermatology market. For instance, PLLA, calcium hydroxyapatite, and PCF. And everything that we've seen here is much far greater and much better than the stimulation that is seen with the others. So finally, and I don't have so much time, periodontal disease. So we have products for treating periodontal disease, which is the largest, probably the largest degenerative disease out there. We are able to treat both the bone, which is lost, and the soft tissue, and I'll show you quickly. We've developed two products. Actually, it's one product, but two different shapes. One is the furcation to elevate the horizontal bone loss, and the other one is vertical. It's implanted there, and then we can measure the probing depth. This was published in Frontier, a veterinary clinical study that was ran in Europe by key opinion leaders there, and the results are really unprecedented. We've seen 100% improvement over the standard of care in the recovery of the soft tissue and the bone. Finally, the last subject, so far I've spoken about just implants without any cells. We've also tried this with cells, for instance, a collaboration with a Japanese pharma company. They took our scaffold, they added those adipose-derived luciferase labeled mesenchymal stem cells, they injected to the dermis, and they've looked what happens with the cell foam and without the cell foam. And cells, well, I'm sure most of you have some experience with in vivo injections of therapeutic cells. They die, they don't survive, they don't engraft very well. Here too, the cells died after a few days. But with the cell foam, they really survived until the study was terminated. So we've also extended that into another more complex system, treatment of macular degeneration. In this case, the retinal pigment epithelium cells are destroyed, and they are in charge of maintenance of the photoreceptor cells. So once they die, we get blindness, and this is the leading cause of blindness. So we took RPE cells from mesenchymal, from isolated from autologous fat, and you can see the wild type, the undestroyed, the untouched retina. You can see what happens when the model is induced, the retina is destroyed. Then RPE alone, the effect is marginal, but when combined with the cell phone, we've seen recovery, full recovery of the retina. So that can be a therapeutic to macular degeneration and unmet need, which already we've discussed that. So I'm almost finished. So, in summary, we've developed a breakthrough technology. We have a focus on our clinical and veterinary applications, but we are very open to collaborate with anyone here. There is so much potential here yet to be explored and you know, it's a broad platform, the cell phone technology, and we'll be happy to collaborate. You're welcome to visit our booth. And finally, just acknowledgement to my team, 6 years of work, very intensive and very nice atmosphere. Our company is in Yokna, by the way, not far away from here, and thank you very much.